Hi, this is Professor Dorr, and this is lecture number 22 of EE310, the inverse Laplace transform. In this lecture, we're going to cover section 15.4 of Alexander and Sadiku's textbook, Electric Circuits. And in this lecture, just like in the last lecture and just like in the next couple of lectures on Laplace transforms, we're going to use the Laplace transform roadmap graphic that I came up with that I really like using in my classes. You might remember in our last lecture, we took a whole bunch of Laplace transforms. We went from the time domain to the frequency domain. Time domain, Laplace transform, went to frequency domain. We did that over and over again, and we learned how to use the Laplace transform tables, we learned how to use the integrals for Laplace transforms, and we learned how to use the properties. But we really spent the whole lecture going from here to here and here to here. In this lecture, we're going to cover the inverse Laplace transform, which means we're going to go from the frequency domain over here up to here, and from here to here, and from here to here. And you might wonder why we skipped the system, but in the next couple of lectures, you're going to find out that you already know a whole lot about how to do this because you know how to make transfer functions. So now that we know where we are, where we're going, what little piece of this big picture we're going to try to do, we're going to focus on the steps for doing inverse Laplace transforms. And the concept that I like to use for my students is that we have guarantees when we do inverse Laplace transforms, because we're always asked to do inverse Laplace transforms of great big ugly transfer functions. But depending on what's in that transfer function, we have certain guarantees. I like to think that real smart people came up with those guarantees, because I sure as hell didn't. But those guarantees, once I know my guarantee, I just have to fit in the pieces because I know the guarantee will work. And that guarantee is, or those guarantees are the little pieces of partial fractions that we're going to use. You've probably seen partial fractions, but we're going to cover those in this lecture. We're going to cover them in a couple of ways. One way is the residue method, which is kind of a traditional method of doing partial fractions. I don't love it that much because when the functions get a little more complicated, like when you have repeated poles, quadratic poles, things like that, it gets a little harder to use the residue method. So in this lecture, I'm also going to show you the method of algebra, which always works. It can be a little more work sometimes, but it always works. So I really like the method of algebra. But basically the idea is we're going to take big complicated functions here. We're going to use our guarantees to break them up into little Lego blocks. And then we're going to take the inverse Laplace transforms of very simple functions. And of course, we're going to augment the lecture with lots of examples so you guys can get familiar with this stuff. All right. So our Laplace transform that we defined in the last lecture was this integral. And here's our definition. It's equation 15.1, first thing we hit in the chapter. Now, let's do something similar for the inverse Laplace transform. And here is our equation. And we look at this equation, at least I do, and we go, eh. And I put a big international band sign around it and say, you know what, we're not going to use that. They use that in the math department, and it's that way. So instead, what we're going to use are the Laplace transform tables and the properties in tables 15.1 and 15.2. So just like we use the Laplace transform table to go from time domain to frequency domain, here, we're going to break complicated functions into simple functions, and then we're just going to use the exact same table, but we're going to go backwards through it. So here is our basic strategy. we're going to be given f of s, which is a great big transfer function, or at least it's reasonably big. And we're going to decompose f of s into a sum of just simple terms using partial fraction expansions. Then what we're going to do, once we have all these little partial fraction terms, we're going to go into the Laplace transform table and just read their inverse Laplace transforms right from the table. So the trick here is breaking up complicated things into simple things, and that's really what this lecture will focus on. So here's our strategy. We're going to start off with this great big transfer function that I keep mentioning. And we are going to call it f big of s. And it's going to be basically a big polynomial. Now you might say, but wait a minute, it's a bunch of little terms multiplied together. Right, multiply them together, you got a great big polynomial. And you got a polynomial on the top, and you got a polynomial on the bottom. And then what we're going to do is we're going to say that the inverse Laplace transform of f big of s, the inverse Laplace of f big of s, is going to be the inverse Laplace transform of f little 1 of s plus the inverse Laplace transform of f little 2 of s plus blah, blah, blah. So the partial fraction technique is what broke f big into f little. Then we're just going to take the inverse Laplace transforms of all our little terms. And when we do that, we're going to end up with f big of t, which is the inverse Laplace transform of f big of s. And f big of t is going to equal f little 1 of t, or in other words, the inverse Laplace transform of f little 1 of s, gives us f little 1 of t, plus f little 2t, plus f little 3t. And this really just shows exactly what we're going to do. Big transfer function, break it up into little transfer functions. Take the inverse Laplace of each one, add the bunch of them together, be thankful for the linearity property, and you're done. So now let's dig into f big and see what it can be composed of. So we'll kind of focus on the denominator for right now. And so f big consists of a numerator divided by a denominator, which of course can be factored. Of course, if we multiply all these factors out, we get our big old polynomial. But we want to focus on the kinds of factors because we're going to need to handle them differently when we do our Laplace transforms. So we'll call these simple poles. S plus P1, S plus P2. And what you can see, if we were going to plot these poles or plot the roots on the complex plane, these would be on the negative real axis. And we call them simple poles. The next kind of factor we could have are repeated poles. In other words, we have S plus P, but it's repeated multiple times, in this case, n times. And you're going to see that just as we have a special guarantee for simple poles, we're going to have another guarantee for repeated poles. Different guarantee, so we've got to be careful. And then finally, we're going to have complex poles. Now, the difference between this expression and maybe two of these multiplied together is that this expression has complex roots. So if we were to plot the roots for this expression on the complex axis, we would have a negative real part, and then we'd have these conjugate imaginary parts. So the poles would be a up in the second quadrant and down in the third quadrant if I have my quadrants right. But they'd be conjugates. And that's the difference between two simple poles multiplied together and complex poles. And just to digress a little bit, I will make comments as we go through the problems of whenever you see a factor like this, try to factor it because it may just be two simple poles. And then it's a different animal than if this function had complex roots, complex poles. So let's handle our cases. We've got our simple poles, our repeated poles, and our complex poles. Let's look at simple poles. And here we're going to hit the first of our guarantees. And here's the guarantee for simple poles. We've got a numerator up here. And mathematically, we can talk a lot about what numerators are acceptable. But what's good enough for me is any real problem in electrical engineering, any circuit problem, the numerator will be such that this will work. Mathematically, it's kind of a cop-out, but it works to get us through EE310. Here's the guarantee. If I have simple poles, I can represent this transfer function as K1 over S plus P1 plus K2 over S plus P2 plus K sub n divided by S plus P sub n. So this is a guarantee. I know that I can pick constants K1, K2, all the way to Kn that will make this, these two functions be equivalent. And if we want to look ahead around the next corner, look how easy the inverse Laplace transforms are for these. They're the simplest ones we know of. Now that we have our guarantees, let's solve for our constant, K1, K2, etc. And the first method I'm going to show you to do that is called the residue method, which is just incredibly elegant and simple and a very beautiful thing. And here's how it works. What I'm going to do is I'm going to multiply both sides of my guarantee function by S plus P1. So on the left-hand side, I'm going to get S plus P1 times f of s. And on the right-hand side, I'm going to get I'm going to multiply each one of these factors by S plus P1. So let's see what we end up with. Well, first of all, when I multiply f of s by S plus P1, it's going to cancel with the S plus P1 in the denominator, isn't it? And when I multiply the right side by S plus P1, I'm going to end up with K1, of course, all by itself over here, and then all these other ones multiplied by S plus P1. So now what I can do is, remember, this S plus P1 canceled out. So if I now set S equal to minus P1, then look what happens. This term goes to 0, this term goes to 0, all the terms go to 0, and I'm left with just K1. So that means that I'm going to solve for my value of K1. So in general, what we say is that K of I being 1, 2, or 3, or whatever, is equal to S plus Pi times f of s evaluated at S equals minus Pi. So here is our statement of the method. And I find that sometimes my students, sometimes they even remember the method from their calculus or algebra class or whatever, but I really hope that you'll remember it with just this beautiful little explanation or derivation showing what it is. Because it's really a clever thing. It's very simple. But this is what it boils down to. And so let's say we do this for all of our i's. We do it, we get K2, we get K3, we get all of our k's here. Look at our inverse Laplace transform. We know that the inverse Laplace transform of 1 over s plus p1 is going to be just e to the minus p1t. K2 is going to be e to the minus p2t. We pull that right out of the table. So let's do an example. Our f of s is equal to 2s plus 4. We'll trust that it came from a circuit problem, so I'm just going to trust the numerator to be a good numerator, and it is. So what we'll do, let's get K1 first. And we're going to use our formula here. And we're going to say K1 is equal to S plus P1. That means S plus 3 times F of S, and we're going to evaluate that at S equals minus P1. So here we go. S plus 3 times F of S evaluated at S equals negative 3. So here's S plus 3 times F of S, and we can see that these two terms cancel out, and we're left with just 2s plus 4 divided by s plus 7. So let's substitute minus 3 into that. And we get 2 times negative 3 plus 4 gives us minus 2. Negative 3 plus 7 gives us 4. K1 equals negative 1/2. Now let's get K2. Again, we're going to use this formula, but we're going to use I equals 2. And so K2 will equal S plus 7. That's our P2 is 7 here. So S plus 7 times F of S evaluated at S equals minus P2, or minus 7. And so when we do that, we're left with our 2s plus 4 on the top, but now our s plus 7 cancels out, and we're left with just the s plus 3 on the bottom. So now what we'll do is we'll substitute in s equals minus 7. We substitute that here. We get 2 times negative 7 is negative 14 plus 4 gives us minus 10. And negative 7 plus 3 gives us negative 4. And we get K2 equals 5/2. So F of S, when I put it all together and use my guarantee, I can say that our transfer function that we started off with, and we were guaranteed that we could represent by this function here, is big transfer function, K1, negative 1/2 times 1 over s plus 3, plus K2 times 1 over s plus 7. And from here, our Laplace transform is trivial. It's the easiest Laplace transform in the table, or inverse Laplace transform. And so f of t, we just put our K1 here, e to the minus 3t plus K2, e to the minus 7t, u of t. So here is our inverse Laplace transform of this function. Let's make sure we know where we are on the roadmap. Here was our big function of s. We just did an inverse Laplace transform to convert it back to a function of t. All right, so we have our time domain function. Can we check it? Because we could have made a mistake, of course. And we can check it. And we check it with the initial and final value theorems that we discussed in the last lecture. Let's just review where those fit again. What the initial and final value theorems do is they say, in English, you've got a Laplace transform and you're thinking about converting it to a time domain function. If I do a full inverse Laplace transform, I'm going to get a time domain function that I can evaluate at 0 or 13 or 17 or infinity, whatever I want. But I'm going to have to do a lot of work to do that full inverse Laplace transform. But if I just want to know the time domain value at 0 and the time domain value when t is equal to infinity, I can do those by just taking some limits. So that's why we call it the initial value theorem, meaning the value of the time domain function at 0, and the final value theorem, which is the value of the time domain function at infinity. So what we just did in our problem is we got the full inverse Laplace transform. So what I want to do is see what the initial and final value theorem give me, and then just see if they match what my time domain function gives me. And if they do, okay, Bella, out you go. Bella doesn't want to go out. Oh, come here, you awful cat. Say hi to my students, Bella. Say hi to my students. Usually when I give these lectures, Bella's down there under my feet. You would think this kitty would know something about electrical engineering, but she doesn't know a thing. She just meows and meows, and she can tell you everything she knows in about 5 of those meows, and then she just starts saying it all over again, don't you, Bella? All right, so what we're going to do, we got our full time domain function for the inverse Laplace with the inverse Laplace transform. Now we're going to do the initial and final value theorems just to see if they check and they agree at t equals 0 and t equals infinity. So the initial value theorem said, actually first, let's evaluate our function at t equals 0. Here's our function. This is going to turn into 1. This is going to turn into 1. So we're going to have, minus 1/2 plus 5/2 equals 2. So that's what our time domain function gives us. Let's use the initial value theorem. Here it is. The little f of t equals 0 is equal to the limit as s goes to infinity, time, frequency domain being the inverse of each other like we talked about in the last lecture. Limit as s goes to infinity of s times f of s. So here's f of s multiplied by s. Let's take the limit as we go to infinity. So I'll multiply this out and I'll get 2s squared plus 4s. I'll multiply this out and I get s squared plus 10s plus 21. And I'm just going to worry about the highest degree s's. And I end up with 2s squared divided by s squared. That's 2 times infinity together, 2 times infinity squared divided by the same infinity squared. Don't tell the math department that. That gives you 2. So take a look. It checks. Now let's use the final value theorem. And so at infinity, the function that we got will give us 1/2 times e to the minus infinity. That's 0. Plus 5/2 e to the minus infinity, that's 0. So now let's use the final value theorem. F of infinity is equal to the limit as s goes to 0 of f of s. Remember, initial and final value theorems, sf of s stays the same. It's just what s goes to. That's the difference between the initial and final value. So here's our s, f of s. And we will substitute in 0, 0, 0. So I got 0 on the top, zeros, and I got something on the bottom. 0 over something gives you 0. So the initial value and the final value both agreed with our inverse Laplace transform, so I'm feeling pretty good about our solution. Now let's look at the second type of situation that we see in partial fraction problems, which are repeated poles. And just to make sure we know where we are, let's go back and look at our basic strategy here. And what we can see is that we had simple poles, and we just learned how to handle those with partial fractions. But then we have repeated poles, and that's what we're going to do now. So again, thankfully, we have smart people who have given us a guarantee. Here's the guarantee for repeated poles. And here's the mathematical definition, or the formal description. F of s can be broken up into k sub n divided by s plus p to the n, because remember the repeated poles, we have n of them, plus another constant times s plus p to the n minus 1, all the way down to just s plus p. So it just depends how big S is, how many of these you have. And then plus the remaining part of f of s, meaning the poles that are not repeated poles. So let's do an example. Here's our f of s, and we can see that we have a repeated pole, and then we have a simple pole. So we have repeated poles right here and simple poles. So let's go to our guarantee. We have k, we'll say k2 divided by s plus 4 squared, that comes from here, plus k1 divided by s plus 4. In other words, we only had two poles, so we only have two terms here. So k2 over s plus 4 squared plus k1 over s plus 4. And then we have this remaining part that is not a repeated pole, our s plus 1. So here's our f, here is our remaining part. We say that's just going to be k3 over s plus 1. So we're going to use the equation in the book, and I'm not going to derive this, but for k2, we actually can do it as a simple pole pair, and here is our equation. k2 is equal to s plus p squared times f of s evaluated at s equals minus p. And if we just go back to the previous definition, we can see exactly how this works. And let's go ahead and just do it. Our s plus 4 squared is going to cancel out with this s plus 4 squared. And we're going to substitute in negative 4. So 8 times negative 4 plus 3 is negative 29. Negative 4 plus 1 is negative 3. And we get k2 is equal to 29 over 3. Now we're going to use equation 1556 to get k1. And here is the equation that we're going to use. Next, we want to get k1. And we can see that the simple residue method won't necessarily work here, because if we multiply everything out by just s plus 4, I'm going to end up with another s plus 4 here, and I'll get a 0 in the denominator. So it's all going to blow up. So the book gives us equation 15.56, which involves doing a derivative. Not going to derive it, but it's a nice little derivation in the book. And here is the formula for getting k1. So what we're going to do is say k1 is going to be equal to d ds 8s plus 3 divided by s plus 1, because you notice the s plus 4 squared has canceled out. And we're going to evaluate that at s equals minus 4. Now, I can only remember the product rule. I never remember the quotient rule. So what I'm going to do is say, this isn't really a quotient. This is a product. And up here, I have s plus 1 to the negative 1. Then I just have to remember the one product rule. I think they call it the chain rule. And so the derivative of this is 8 divided by s plus 1. And here, my derivative here is going to be 1 multiplied, is going to be negative 1 over s plus 1 squared multiplied by 8s plus 3. So there's my derivative, and I'm going to evaluate that at s equals negative 4, and I get k1 is 5/9. So now I've got this pole, I've got this k2, and I've got k1, but now I need to get k3. And I see that k3 is nothing but a simple pole, so I can go back and use the residue method again. So easy. It's just s plus p times f of s evaluated at s equals negative p. Or in other words, s plus 1 times f of s. The s plus 1 is factored out here. And I substitute s equals negative 1. And I get negative 5/9 for k3. So we started off with this f of s. It had a repeated pole, so we had to do our special little derivative thing to get one of our constants. But here it is as simple little Lego building blocks in the frequency domain. This Laplace transform is right in the table, as is this one, as is this one. We use that table, and we get 29/3 times t times e to the minus 4t plus 5/9 e to the minus 4t minus 5/9 e to the minus t. So now let's check our work. At t equals 0, let's look at what our function gives us. It's going to give us 0, because I got a 0 right here for this t, plus 5/9 minus 5/9 is equal to 0. So that's what our function gave us. Now let's spot check t equals 0 with the initial value theorem. So little f of 0 is the limit as s goes to infinity of s times f of s. And that's going to be the limit as s goes to infinity of s times 8s plus 3 over more s's down here. And I say, hey, the degree of s is 2 here. The degree of s in the denominator is 3. So it's going to 0. So quick little spot check just to help me out there. So now we've seen the residue method, and we found that it was really easy to use it for simple poles, but it got a little more complicated when we did repeated poles. Now the residue method was great back when I went to school, and we barely had 4-function calculators, and we didn't have a calculator that could compute matrices. And so we liked the residue method, and we got pretty good at it. But I really like the method of algebra, which I'm going to show you now. And we can solve any partial fraction with this. It's a brute force method, including complex poles, which we haven't covered yet. Sometimes it's easier, and sometimes it isn't. The thing I like about it is it works the same way every time, so I don't have to remember a whole bunch of things. All I need to know is my guarantees. Remember, my guarantees tell me what the function will look like when it's split up. And you remember how the simple poles, the guarantee we have there, which is what we're using right here, was different than the guarantee that we had when we had repeated poles. So the way I really like to do these partial fraction problems is I look at my f of s and I figure out what guarantee applies, or in other words, what does the right-hand side of that equation look like? And then I use the method of algebra, which we're going to do now. So what let's do is let's go back to the first example that we did and do it with the method of algebra. Our S-domain function was 2s plus 4 divided by s plus 3 times s plus 7. And our guarantee is that we could represent that as k1 over s plus 3 plus k2 over s plus 7. So look at this equation. It's guaranteed. I just got to solve for k1 and k2. So here's what we're going to do. We're going to put this side over a common denominator. And the common denominator will be s plus 3 times s plus 7. You may say, why are you going to do that? Because if they're both over a common denominator, I can blow off the denominator and just equate the numerators. So I'm not doing this blindly. That's why I'm getting my common denominator. So 2s plus 4 divided by s plus 3 times s plus 7. That's on my left. And now what I want to do is put these over a common denominator of s plus 3 times s plus 7. So I got to multiply k1 by s plus 7. And I got to multiply k2 by s plus 3. And here we go. So here is my right-hand side over a common denominator. Now let's kind of multiply things out so we can see what we're doing. And now what we're going to do is we're just going to equate the numerators. That's why I put them over a common denominator, because see how I can just blow off this denominator now. I got to pick k1 and k2, so this equals that. You see that? I got to pick k1 and k2, so this numerator equals that numerator. Now you might say, wait, professor, you only have one equation, you have two unknowns. But I'm going to do what the seagull does. And I'm going to say, I got s terms, and I got s to the 0 terms. All the s terms got to add up to be 2, right? That means k1 plus k2 better equal 2. And my s to the 0 terms better equal 4. So let's see. 7k1 plus 3k2 ought to equal 4. Do you see how I just broke this into two equations and two unknowns? Because I equated my s terms and my s to the 0 terms, meaning no s in them. So let's do that. 2s plus 4 is equal to k1s plus 7k1 plus k2s plus 3k2. I just equated the numerators. Let's factor out the s terms. So here I have s times k1 plus k2. And now let's gather up my s to the 0 terms, which are just 7k1 plus 3k2. And I know that these s terms have to be equal to 2. And my s to the 0 terms have to be equal to 4. So k1 plus k2 equals 2. And 7k1 plus 3k2 equals 4. And I have two equations in two unknowns. And I slap that into my calculator. I got to be honest, I use MATLAB. You guys all have to use calculators. And I get the exact same answer I got before. Now, look at this. It's a little more work than the residue method. So you have to pick whether you want to do a simple pole problem this way or use the residue method. I tend to do it this way, but I always have MATLAB in front of me, and I'm real old, so I don't have to take exams anymore, so I don't have to worry about doing it 30 seconds faster one way than the other way. Let's go to our second problem using the method of algebra. Now you remember in this problem, we had a repeated pole. We had this s plus 4 squared, and that kind of caused us some problems because we had to do a derivative, and it's pretty easy to make a mistake when you do a derivative, and we had to remember that derivative formula, and I'm like, to hell with that. What I'm going to do, I'm going to remember my guarantee. Here's the guarantee for repeated poles. And up above, I showed you the general form of the guarantee, but here we only have 2 poles, so I'm going to show you just the specific form when we have 2 poles, which are k2 divided by s plus 4 squared plus k1 over s plus 4 plus k3 over s plus 1. Some smart person figured this out, but for me, it's a guarantee. Thanks for the guarantee. I'm going to go solve electrical engineering problems. So exact same thing as before. Let's put both of these over a common denominator, and of course this is going to be the common denominator. So this first term, I need to multiply it by s plus 1. This term, I need to multiply it by s plus 4 and s plus 1. This term, I have to multiply by s plus 4 squared. So here it all is. And they're both over the same common denominator, so that's the end of the denominator. I'm not going to worry about it. Let's multiply this numerator out. And I do all my multiplying out, and I grind through the math, but what I'm trying to do is separate out my s squared terms, my s terms, and my s to the 0 terms, because those I can equate to the terms over here. And here we go. S squared, I don't see any s squared terms here, so the s squared terms over here better add up to 0. My s terms add up to 8. My s to the 0 terms add up to 3. And so what I end up with is a 3 by 3 matrix, because I really have 3 equations in 3 unknowns. Is this cool or what? I think this is really cool. We get K1, K2, K3. We didn't have to remember all that derivative business. All we needed to know was our guarantee, and then we just plugged our way through the method of algebra, and our reward was we got to solve a 3 by 3 matrix in the end. So method of algebra is pretty cool. It's obvious I'm quite a proponent of it. All right, so now let's put some stuff together. I want to find the response of an RC circuit to a unit step. Here's my problem. I want to take this little RC circuit here. When we're working it using these for AC circuits, we said, ooh, that's a low-pass filter, because we could see our capacitor here, and our asymptotic analysis said this was a open at low frequency. It's a short at high frequency, so this passes low frequencies, but it doesn't pass high frequencies. That was frequency domain, frequency response. What I want to find is I want to shove a step in the front end of this thing, and I want to see what comes out the other end. Let's just kind of triage it. I know I can't change the capacitor voltage quickly, right? So when this step hits, this is going to be 0 over here, because I can't change this voltage quickly, and I start off at 0. But I know after I wait for a while, this is going to end up having a transfer function of 1, because this will end up as an open circuit, So I got no current here, so this voltage will equal this voltage. So at 0, I'm going to have 0. At time equals infinity, I'm going to have 1. Here's a sketch of it. Looks reasonable. It's a simple enough problem that you certainly don't have to use Laplace transforms. If you buy this fine book right here, then you will see a little formula in there that takes all your initial conditions into account for these first order kinds of systems and gives you an equation that works first time and every time. But we are going to walk before we run, so we're going to solve this problem with Laplace transforms. Let's put it on the roadmap. Here's our time domain input. It was our little unit step, and let's put it right up where it belongs. Now what I'm going to do is I'm going to take its Laplace transform, and I'm going to put it in the frequency domain. We go to our table of Laplace transforms, and we go, oh, duh, that's 1 over s. And now we're going to go somewhere we haven't gone before, but we already are pretty good with this. We know the transfer function of this thing. So in order to get the Laplace transform of the output, drum roll, we just multiply the Laplace transform of the input by the transfer function. Let me say that again. In order to get the Laplace transform of the output of the circuit, we just multiply the Laplace transform of the input, which is our 1 over s, by the transfer function. And so sitting over here, we have the S domain representation of the output. So now what we got to do is just do the inverse Laplace transform, and we'll get the time domain output. So this is a very classical kind of Laplace transform circuit problem. We get the Laplace transform of our input signal. We multiply it by the transfer function. That's why I show multiplication here. And then we invert the result, and out pops our time domain response. So now you can see what we're doing on the Laplace transform roadmap. Let's do it. So our strategy is going to be, we're going to get the Laplace transform of our input. It's 1 over s. It's an easy one right out of the table. We are going to compute the transfer function for the circuit, VO of s divided by Vn of s. That's right here. We are going to multiply the Laplace transform of the input by the transfer function. That's going to give us the Laplace transform of the output. That's going to put us right here. Then we're going to invert the Laplace transform of the output to get the time domain representation of the output. Or in other words, we're going to go like that. Of course, since Professor Dorr is involved, chances are good that we'll do the initial and final value theorem, partly to check our work and partly because I just think they're so cool and they're going to help you so much when you get into control systems. All right, so we already have our Laplace transform of the input. Let's get the transfer function for the circuit. We've done this a few times, right? Let's do it again. It's just a voltage divider. It is going to be V out over Vn equals 1 over Sc divided by 1 over Sc plus R. We'll multiply top and bottom by Sc, and we get it 1 over 1 plus SCR. And then what I'm going to do is I'm going to kind of wiggle the format around just so it'll look nicer when I do my Laplace transform inversion. Now, if you don't do this, you'll figure out that you need to when you get there, but I'm just doing it in advance because I've kind of seen this movie before. So here's a transfer function. So the Laplace transform of the output, or in other words, this is going to be the Laplace transform of the input, 1 over s, multiplied by the transfer function. Laplace transform of the input multiplied by the transfer function, 1 over s times 1 over RC times 1 over s plus 1 over RC. Here it is right here. So now we're going to use we're going to invert the Laplace transform of the output. We're going to invert this rascal right here, and that is going to give us our output signal in the time domain. And we're going to use the time integration property. Why am I using that? Because I see a nice, easy Laplace transform multiplied by 1 over s. And so what I can do is I can say that if I have a Laplace transform that is 1 over s times f of s, then I'm going to say that I can get the inverse Laplace transform of f of s and then just integrate it from 0 to t. This is my property right here. Okay, so the Laplace transform, inverse Laplace of 1 over f of s is equal to this integral times the inverse Laplace transform of f of s dt. Now, this might look a little funny to you, but it's a very nice way of giving you an equation showing how the property is used. So if this is a little confusing to you, stop the video and kind of check it out, because this makes absolutely good sense and it'll help give you an idea of how to use the properties. So my out of s is going to be 1 over RC, that's constant, times 1 over s, there it is, times 1 over s plus 1 over RC. So let's say that f of s is going to be just 1 over s plus 1 over RC. And that has a really easy Laplace transform. It's just e to the minus t over RC. So now that I have my inverse Laplace of f of s, I just need to do the integration. So this integral sign is that integral sign. And this is an easy integral to do. Even I can do this. So it's going to be 1 over RC times minus RC times e to the minus t over RC. The RC's cancel, and I get minus e to the minus t over RC minus 1. Let's straighten those negative signs out. I get 1 minus e to the minus t over RC. Now, I'm going to check this. And I know that when we triage this problem, the value of the time domain function at 0 is going to be 0. We did that by just saying you couldn't change the voltage across the capacitor quickly. And so let's look at our function. 1 minus e to the 0, that's 1 minus 1. Good. The output at time equals 0 is 0. Now let's set t equal to infinity, and this term goes away and I just get 1, which is just what I calculated above. And I didn't use the initial and final value theorems, though if you know all the trapdoors of EE310, you really did. But I just looked at what the circuit did, said, hey, what's it going to do at time equals 0? What's it going to do at time equal infinity? And then I made sure that my function did that. And when I set up above that I was going to specifically use the initial value and final value theorem, I lied. Sorry. Let's move to our next example. And in this example, we have an op-amp. And I want you to recognize the topology of this op-amp. So take a look at that and think about our topologies. We have the inverting op-amp, the inverting topology, And we have the non-inverting topology. And here what I see is my input is going into the plus terminal, which suggests the non-inverting topology. And I see R2 is equal to 0, and R1 is equal to infinity. And I have a special case of the non-inverting topology called the voltage buffer. In other words, the voltage here will be recreated here. Now, we've mentioned this a few times in lectures, but I want to pound it in a little deeper. You might say, well, gee, Professor, why do you need an op-amp if the voltage here is the same as the voltage here? And here's why. Because there's no input current on this op-amp. So there's no current here. So I am not loading down this network. But out here, I'm going to have the same voltage, but I can put out whatever current I need. See that? That's why we call it a voltage buffer, because it's going to take this voltage here and just sniff it. It's not going to change. It's not going to affect the circuit because it's not taking any current. So I just call it a sniffing point. So it sniffs this voltage, puts that voltage here, and this sucker has like a Thevenin resistance of nothing. So it can put out all the current it needs to put the voltage, to make the voltage correct here. Now, a good thing that you could ask is, hey, wait a minute, no current here. How can I get a big current coming out of here? And I said, oh, well, I didn't show you the power supply terminals because we don't do that in EE310. But if we want to make KCL work around the whole op-amp, you got to show the power terminals. But really important that you know why voltage buffers are there. They sniff this voltage, and then they produce that voltage right here with no Thevenin output impedance out of this op-amp. If you're taking EE330 or your introductory microelectronics class, kind of like an emitter follower, isn't it? The emitter just follows that base 7/10 below like a little dog. So it's a voltage buffer. All right, so here's our circuit. We've got a unit step here, and we've got a little RC thing going on. And we know that we're not loading that RC down with this op-amp. So analysis-wise, we could kind of do this really by itself if we wanted. And then out here, whatever this voltage is going to be, it's going to drive this. So we're going to get some little smooth thing. And that's going to go to the inductor. So let's see, what's V out at 0 plus? Well, at 0 minus, let's say that this capacitor is going to be at 0 volts. Now you could say, well, at 0 minus, the whole circuit's dead, but I don't like doing that. I like saying that at 0 minus, this U of t is giving you 0 volts. So if there were any voltage on the capacitor, you'd get a current, and it would flow this way until there was no more charge left in the capacitor, and the capacitor would be at 0 volts. So at t equals 0, 0 minus and 0 plus, I'm 0 volts here. So that means at t equals 0 plus, I'm 0 volts here. So it's not going to do anything here. So I'm going to have 0 volts here at t equals 0 plus. Now let's look at V out of infinity. So at infinity, I know that this is going to be 1. I'm going to have no current in the capacitor because I'm at steady state. And I got no current going into my op-amps because that's what op-amps do, or don't do, I guess. So no current here, no current here. KCL on the fly says no current here. Got 1 volt here, no current. 1 volt minus 0 current times resistance gives me my 1 volt here. Or in other words, I got no voltage drop here. So that gives me 1 volt here. And then I say, oh, darn, at t equals infinity, that's steady state, and there's going to be no voltage across that inductor, so I just wasted my time with everything I did over here. But I got a lot smarter. So V out of infinity is 0. And now that we look at it correctly, we say the reason for that is because there's no steady state voltage across this inductor. I don't care what's going on back here. Okay, so now the Laplace transform of our input, or before we do that, let's go back again to the Laplace transform roadmap. What we're going to do is we're putting a unit step into the circuit. We are going to get the Laplace transform of our unit step. We're going to multiply it by our transfer function, and then we're going to invert the Laplace transform to get the time domain output. So when we look at our laundry list of things we got to do, we have to get the Laplace transform of the input. That's pretty easy. It's a unit step, so it's just 1 over s. Ooh, but we got to get this s domain transfer function, so we can multiply it by 1 over s and then get our value here. And then we're going to have to invert the Laplace transform. And there's a few components there, so it's probably not going to be super easy. So the work in this problem is we're going to have to get a transfer function, then we're going to have to invert a Laplace transform. Now, if you look at this circuit carefully, I want you to convince yourself that it's pretty easy to get the transfer function of this circuit, V out over V in. I want you to look at this circuit and figure out why it's easy to get the transfer function. You can thank our voltage buffer for that, because remember, there's no current here. So that means that the transfer function of this piece here, I can get it just with the resistor and the capacitor. And here, I've got a voltage source that is driving this network. So what I can do is I can just multiply those two transfer functions together. So for the first stage, my transfer function is 1 over SC divided by R plus 1 over SC. Gives me 1 over 1 plus SCR. And in the last problem, you saw why I ended up factoring my 1 over RC out. If you didn't, go back and take a look, or just kind of pay attention to the fact that it'll help us here. So here's my first stage. This is the transfer function between here and here. It's V here divided by V in. Now let's go to the second stage. Clean slate. I get to start over again. SL divided by SL plus R. And I'm going to do the same thing. I'm going to put the S by itself here. And you might be saying, hey, that's exactly the opposite of what you did when you were in Bode plot problems. And I'll say, yep, that's the way it works. So here's my second stage. So now to get the transfer, or what this second stage transfer function represents is V out divided by V here. If you want, you could say V out divided by V here. And I just multiply these together, and here's my cascaded transfer function. I want to pound this point in. What if there was just a piece of wire here? Would the transfer function be the same? It would not, because now I'd have current flowing this way from this network into this network, and the whole ball game would change. So even though you might have started this class with the disease of op-amp-itis, this op-amp was your buddy because it made this problem easier for us. So here's our cascaded transfer function. Everybody's multiplied together. So now what I'm going to do, I have my cascaded transfer function. Let's multiply it by the Laplace transform of the input and get the Laplace transform of the output of our circuit. Here it is. We're going to take Vn times h of s, or 1 over s times h of s. And we see we got an s up here, so that's going to cancel with our 1 over s. And here is v out of s. So we look at this transfer function, and we say from here, we have to, on our roadmap, we got to go this way. Got to go this way, really the subject of this lecture. So here is the function we need to get an inverse Laplace transform of. What guarantee do we use? Which one of our guarantees? The guarantee for simple poles. Here it is right here. We're going to say that all this nonsense here is equal to K1 over S plus 1 over RC plus K2 times S plus R over L. And I'm going to use the method of algebra because I like it and because I think matrices are cool. So what I'm going to do is I'm going to put everything over this common denominator. So that means I have to multiply K1 times S plus R over L, and I'm going to multiply the K2 by S plus 1 over RC. And here is what I get. And so at this point, I can throw away my denominators, and here is my numerator. So I can say that K1 times S plus R over L plus K2 times S plus 1 over RC is equal to just 1 over RC, because I just have a 1 here. And so I'll multiply that out, and I have K1S plus K1R over L, blah, blah, blah. I multiply it out. But then I'm going to gather up my S terms, and I have K1 plus K2 times S. I don't have any S terms on the right side, so that equals 0. And now I add up I call them my S to the 0 terms because they don't have the S, because S to the 0 is 1, right? And K1 times R over L plus K2 over RC is equal to 1 over RC. And from there, I have 2 equations and 2 unknowns. And I can't escape numbers anymore, so I actually have to put the numbers in. And I get K1 is equal to 0.25, and K2 is equal to minus 0.25. So here is my Laplace transform of the output broken up into little Lego bricks. And these inverse Laplace transforms are trivial. So we have 0.25 e to the minus 20t minus 0.25 e to the minus 100t. So I would recommend on this problem that you check your answer with the initial and final value theorems. Or remember that when we started the problem, we just looked at the circuit and said, hey, we know what it's going to do at time equals 0 and time equals infinity. Go see if this gives you the same answer. If you really want to study for the final, work this problem as a general RLC problem from Chapter 8. Okay, so that's our lecture on inverse Laplace transforms. Look forward to having you all again tomorrow. And as always, I look forward to seeing all my students in office hour.